Welcome to the Chemistry 209 Masterclass series. This series of lectures is intended to highlight the key concepts of introductory spectroscopy and structure. This lecture, Masterclass 4, discusses the quantum structure of many electron atoms. One of the simplest examples of a many electron atom is helium. Helium has two spin-paired electrons occupying the 1s orbital, which we can describe with a singlet S0 atomic term symbol. This electronic configuration satisfies the Pauli exclusion principle, which may be stated as no two electrons may have identical quantum numbers. Singly excited electronic configurations of helium are more interesting. Now the electrons may either be spin-paired or spin-aligned, which means that the total spin angular momentum quantum number is either 0 or 1. This leads to values of 2s plus 1 equals 1 or 2s plus 1 equals 3, which we refer to as singlet and triplet excited states. To understand where the concept of singlet and triplet states comes from, we must consider a more general form of Pauli's principle. The Pauli principle can also be stated as any acceptable wave function must be antisymmetric with respect to exchange of two identical fermions and totally symmetric with respect to exchange of identical bosons. Here we must remember that fermions are particles with half-integer spin quantum numbers and bosons are particles with integer spin quantum numbers. This applies to the total wave function, so by exchanging two electrons we find that psi total 1, 2 equals negative psi total 2, 1. Viewing the total wave function as a product of a spatial wave function and a spin wave function allows us to consider the effect of spin exchange. If we label m sub s equals plus 1/2 as spin up or alpha spin, and m sub s equals minus 1/2 as spin down or beta spin, we can arrange the two electrons into four spin orientations, both alpha, both beta, alpha beta, or beta alpha. In the first two cases, swapping electron 1 and electron 2 has no effect on the spin configuration. For the final two spin orientations, swapping the electrons is neither a symmetric nor antisymmetric function. Instead, we interconvert between case 3 and case 4. Owing to the fact that the two electrons are indistinguishable, we can take linear combinations of the two final spin wave functions to yield one symmetric function and one antisymmetric function. This gives us a total of four spin wave functions, three of which are symmetric with respect to exchange of the electrons, and one that is antisymmetric with respect to exchange. This is the origin of our singlet and triplet terminology. We can also represent this concept of singlet and triplet spin states diagrammatically. If a magnetic field such as the orbital angular momentum magnetic moment is applied to the spin system, we now know that the electron spin angular momentum will couple so as to align with or against the quantization axis. The spin angular momentum precesses about the quantization axis, and it is the projection of this precession cone onto the quantization axis that we describe with m sub s. For singlet states, the electron spin angular momenta point in opposite directions and precess 180 degrees out of phase with one another, thereby cancelling. For a triplet spin state, both spin angular momenta add to yield the total spin angular momentum of 1. This can be achieved if both electrons are spin up, if both are spin down, or if the electrons have alpha and beta spin precessing in phase. The symmetry properties of singlet and triplet states have important bearing on their relative energies. In general, for states arising from the same electronic configuration, the triplet state lies lower in energy than the singlet. We can understand why this is the case if we now consider the spatial part of the total wave function. Imagine that our helium atom is in an excited 1s1, 2s1 configuration. We can then construct a total spatial wave function that is a product of the 1s wave function for electron 1 and the 2s wave function for electron 2. However, like we saw for the alpha-beta versus beta-alpha spin configuration, exchange of the two electrons yields neither a symmetric nor an antisymmetric spatial wave function. Therefore, we must generate symmetric and antisymmetric linear combinations of the atomic orbitals. Now recall that the spatial wave functions for triplets are symmetric with respect to electron exchange. Since the electrons are fermionic particles, we must pair the triplet spin wave function with the antisymmetric spatial wave function to satisfy the Pauli exclusion principle. So, electron exchange changes the sign of the triplet spatial wave function. But think about what this means as the two unpaired electrons approach one another. If we could somehow squeeze both electrons into exactly the same spatial position, the spatial wave function would equal the negative of itself. This can be true if and only if the value of the spatial wave function is 0 under this condition. Stated in another way, there is zero probability of finding two electrons in the same region of space if they are described by an antisymmetric spatial wave function. This probability dip for an antisymmetric spatial wave function is known as a Fermi hole. Conversely, we find a slight maximum in the probability of finding two electrons in the same region of space if they are described by a symmetric spatial wave function, and this is termed a Fermi heap. In other words, the electrons are correlated. Their location depends on one another. For triplet states, the reduced probability of finding two electrons at the same location in space also means that the electron-electron repulsion is slightly reduced. Singlet states, on the other hand, exhibit a slightly higher degree of electronic repulsion owing to the Fermi heap. As a result, the triplet state is lowered in energy and the singlet state is raised in energy. We can describe this energy difference quantum mechanically with the exchange integral. As a result of electron correlation, the excited triplet terms of the helium atom are at a slightly lower energy than the excited singlet terms. Consequently, we observe an emission spectrum associated with the singlet states and a different emission spectrum for the triplet states. These transitions obey the same selection rules as those of the hydrogen atom. However, owing to the multi-electron nature of helium, we also find two new selection rules. For any transition, the electronic configuration can only change by the excitation or relaxation of a single electron, and transitions can only occur between terms with the same multiplicity. To summarize what we have learned about atomic structure, an electronic configuration gives rise to terms that can occur at different energies owing to the electrostatic and spin correlation interactions. These terms can then split into energy levels owing to the magnetic interaction associated with spin-orbit coupling. There are two J+1 quantum states associated with each of these levels, which are degenerate, or at the same energy, under zero field conditions. We'll see in a few slides that this quantum state degeneracy can be lifted through interaction with external magnetic or electric fields. It is important when predicting terms from electronic configurations to be conscious of the fact that not every conceivable term occurs. For example, if we consider the 1s2, 2s2, 2p2 electronic configuration of carbon, we might naively expect to find singlet and triplet s, p, and d terms. If we think a little more carefully about the triplet d term, though, we find that both valence p electrons must have the same quantum numbers for this term to arise. This, of course, violates the Pauli exclusion principle. A sure way to determine which terms are possible is through constructing a microstate table to show each possible combination of quantum numbers and then assigning these states two appropriate terms. Upon deducing which terms are possible for a particular ground state electronic configuration, Hund's rules can be applied to determine energetic ordering. Within the Russell-Saunders coupling scheme for a given configuration, the term with the largest total spin angular momentum is lowest in energy. For a given total spin angular momentum, the term with the largest total orbital angular momentum is lowest in energy. For terms with several levels, if the atomic subshell is less than half full, the lowest total angular momentum level is lowest in energy. Whereas if the subshell is more than half full, it is the highest J level that is lowest in energy. This level energy ordering assumes that the spin correlation energy is much larger than the orbital angular momentum coupling, which is assumed to be much larger than the spin-orbit interaction. For the ground state configuration of the carbon atom, this treatment yields a triplet P0 ground state with triplet P1, triplet P2, singlet D2, and singlet S0 excited levels occurring at increasing energies. The two J+1 quantum states associated with each level are all at the same energy if the atom is not subjected to external magnetic or electric fields. As was mentioned previously, this is known as state degeneracy. We now know that the electron orbital and spin angular momenta give rise to magnetic moments, and that these magnetic moments can interact with an externally applied field to lift this degeneracy. For example, consider the case of a singlet term with L greater than 0. In this case, S equals 0, so there is no spin magnetic moment. Thus, J equals L. The alignment of the orbital angular momentum with respect to an externally applied magnetic field is described by the m sub L projection quantum number. If we define the external magnetic field axis as the z-axis, the z component of the orbital angular momentum is given by m sub L h bar. By substituting the quantum mechanical projection quantum number description of Lz into the classical description of magnetic moment interaction energies, we see that each quantum state will interact differently with the applied magnetic field. For a singlet P1 level, the m sub j equals +1 state is raised in energy by an amount minus gamma e h bar b, where b is the magnitude of the external magnetic field. Note that gamma e, the gyromagnetic ratio for an electron, is a negative value. Similarly, the m sub j equals -1 state is reduced in energy by an amount gamma e h bar b, whereas the m sub j equals 0 state energy is unaffected. Thus, the field-free degeneracy is lifted and spectral lines are split by interaction with an external magnetic field. This is known as the Zeeman effect. The interaction between external magnetic fields and singlet states with L greater than 0 is known as the normal Zeeman effect. In the diagram shown here, we see that the normal Zeeman effect causes a singlet D2 level to split into 5 states and a singlet P1 level to split into 3 states. As a result, the single spectral line observed under field-free conditions splits into 3 lines, which are associated with delta m sub j equals -1, 0, and +1 transitions. Remember that because S equals 0, m sub L is the same as m sub j. For states with S not equal to 0, the spin angular momentum gives rise to a magnetic moment that must also be accounted for in our description of the magnetic interaction. This slightly more complicated scenario is known as the anomalous Zeeman effect. Here we introduce another term to our equation, the Landé-G factor, which describes the coupling between the spin and orbital angular momenta. Note that if we apply this equation to the S equals 0 case, where J equals L, we find a G factor of 1, which yields the expression for the normal Zeeman effect. An important distinction that should be noted for the anomalous Zeeman effect when compared to the normal Zeeman effect is that for the anomalous effect, interaction energies, and therefore spectral splittings, are dependent on J, L, and S. As a result, the splitting for a doublet D 3/2 level will be different from that of a doublet P 1/2 level. This difference in interaction energies manifests as further splittings observed in the atomic spectrum. The application of electric fields can also lift degeneracies of atomic and molecular states. This interaction is known as the Stark effect. For atoms, the applied electric field must first polarize the atom prior to interacting with the resulting electric dipole moment. As a result, the Stark effect is somewhat more complex than the Zeeman effect for atomic species, and it has proven to be of limited use for atomic spectroscopy. For this reason, we will not deal with the Stark effect here. We will, however, revisit the Stark effect in Master Class 7, since it is a major tool for rotational molecular spectroscopy. See you next time.